All right, in this video, we're going to look at translations of ordered pairs, or just single points. So it could be just a single point that we want to do a translation on, or a whole set of points that maybe make some sort of shape that we're given. So nonetheless, however many points we want to do, there's a couple different ways that we can describe a translation. So in this video, we will take a variety of kind of ways to approach this. And not only are we going to see different ways to describe the translation itself, but we'll do it two different ways. I'm going to look at more of a visual approach, right, putting it on the graph and seeing what's happening. And then we'll do more of a computational, just working with the numbers to put the values where they belong. Okay. So in this case, we were given three ordered pairs, C, D, and E. I went ahead and plotted them. So if you don't have them plotted, if they give you all of this and you want to take a visual approach to answer this question, then we would want to start by graphing all of these points. And then this is what we'll call a translation equation. It says that if we were given some ordered pair, it gets mapped to a new location. Right? More specifically, any x value in our ordered pair will be subtracted by 3, and any y value in our ordered pair will be added by 8 to get a new ordered pair. So if we think about this visually, if we have an x value, let's say we look at C first, an x value of 2, well, this part of the equation says that whatever my x value is, I'm going to subtract 3 from it. So in terms of one dimension, just x's, if I have an x value of 2 and I subtract 3 from it, that's going to move it in the negative direction of x 3 units, right? Because taking a value of 2 and subtracting it, if you think of this like a number line, is just going to move it to the left. If I were to add values to x, visually, that would move it to the right. Just thinking about this not in 2 dimensions, but only in 1 dimension, right? And then the same thing here. If I took my y value and I added 8, if I think of just a single dimension of y being up and down, whatever my y value is, if I add 8 to it, it's going to increase y and just move it up. If this was a subtraction, I would just, make y smaller by subtracting 8 and moving it down. So I'm going to do both of these simultaneously, right? My x is going to be subtracted by 3, which is going to move it to the left 3 units, right? And the y is going to be added by 8, so I'm just going to add 8, which will move it up 3 units for each one of these ordered pairs. So this ordered pair is going to be moved left 3 units in the x direction and up 8. So I want to do this simultaneously. So left 3 and then up 8. 1, 2, 3, 4, 5, 6, 7, 8. Right? So this is the new location of C. Generally, the notation will be to take your C. You still want to say that it's C because, C gets moved to a new location. And generally, we'll put like a little apostrophe on it. Generally, it's called like C prime. So C prime is moved to a new location. Right? And we're going to do this translation for each point. So I'll take D, and I'll move it left 3 units, and then up 8 from here. So left 3, 1, 2, 3, up 8, 1, 2, 3, 4, 5, 6, 7, 8. So this will be now D prime. E, left 3, 1, 2, 3, up 8, 1, 2, 3. So this is my new E location, which we'll call E prime. So if I just connect the dots here, right, we can see that our original shape just moved 3 units to the left and 8 units up to its new location, right? So a translation is just shifting the shape to a new location. So a translation is what we would call a rigid transformation. Rigid transformations are transformations on ordered pairs that preserve the shape and size of the original figure, right? So a translation is literally just taking this, if this was a like a physical triangle, and I just move it, the shape and the size would not change under this translation, right? Now, if I didn't want to take a visual approach, I could literally just use this equation on these ordered pairs to create their new location, right? So I'm just going to take each of these ordered pairs, right? So we'll say 2 is my x value, and I want to subtract 3 from it, right? Negative 1 is my y value, and I want to add 8 to it, right? So what do we got? 2 minus 3 is negative 1. Negative 1 plus 8 is 7, right? And then, if I wanted to plot this point, negative 1, 7, we can see that it puts it where we already have it. So basically, as we do both of these methods, they should all check out, right? So whether you want to do a visual approach or not, or if you just want to do the arithmetic here to make this happen, each way is fine. So if we take D7, subtract 3 from the x value, negative 4, add 8 to the y value. So what is that? 7 minus 3 is 4, right? And then take E4 minus 3, because my x minus 3, negative 6 plus 8. So 4 minus 3 is what? 1 and 2. And then again, if I plot these points, E is 1, 2, so E prime is 1, 2, and then 4, 4 is D prime. So we can see we didn't really need to make the picture. We could just take the ordered pairs, use the equation, get these ordered pairs where they should be located. So in general, the visual approach is pretty quick. Just, move the points where they belong. It should be an easy check to see if things go right, because if the shape doesn't look the same, then you might have miscounted or something like that. If our ordered pairs were really big and we couldn't put them on a graph, then this method would fall apart, right? So our translation equation can be used if we have really large ordered pairs, x's and y's, that we can't plot, or let's say we had values that weren't very friendly to graph, like decimals or fractions. We can still do the arithmetic and get the locations without needing to bother with partial movements, movements on partial units, right, like fractions or decimals. Okay, so let's try another one. Same thing using the translation equation. Okay, so again, I'm going under the idea that, if we were given all of this, we're going to start off by plotting all of our points. So I went ahead and plotted these preemptively to save time. Okay, and then again, I'm just going to do it visually, and then I'll come over here and I'll do it by hand here. So this is saying that each of the x's are going to be subtracted by 7, so this is going to be a movement to the left because it's going to make our x's smaller. Subtracting a y by 6 will make it reduce, so this will move it to the left 7 units and down 6 units. So each one of these, left 7, down 6. 1, 2, 3, 4, 5, 6, 7. 6 here. 1, 2, 3, 4, 5, 6, 7. 1, 2, 3, 4, 5, 6. Right. And the good thing is with practicing with these shapes, the idea is that if you start off with these ordered pairs, right, if this is something new to you, starting off with these ordered pairs and you plot them, if the shape that you plotted don't look like a square, then you probably plotted the points incorrectly. As we translate these along the equation, again, if our translated points don't look like a square, then we probably miscounted. So that's why I'm using these defined shapes so that everything looks like it's supposed to. So this will be W prime, X prime, Y prime, Z prime, right? Okay. If we wanted to use the equations, we'll take each of the ordered pairs. So 1 Each x is going to be subtracted by 7. Each y is going to be subtracted by 6. So I'm just going to write them all out first. Right? And then I'll just go ahead and put these together. So we got negative 6, 1, negative 1, negative 1, negative 3, negative 6, negative 8, negative 4. Right? And again, if we checked them, right, negative 6, 1, looking good, negative 1, 1, negative 3, 6, negative 8, 4. Yeah, all the points match up. Right? So either way. All right, let's try it out. Okay, so again, they gave us 2 points. It's just a segment, right? You can't really make a shape with 2 points, so we'll just call this line segment AB. Translated along a vector. Now, a vector, if you're not familiar, is like a ray, right? So in terms of lines, right? In terms of lines, we have like a line that goes on forever, right? Like a regular line. We have a line segment, like this guy. An array is just a point, and then it goes in one direction, right? But the difference between a vector and an array is that a line segment, right, ends, array keeps going. That's why the arrows keep going. A vector looks like a ray, where it has a point and then it moves, but a vector will stop at a certain distance. So a vector is like a ray that has a certain direction and what we call magnitude, which is the length of the line, right? So a vector might look like this, and this vector would actually be different than this vector, where they both are going in the same direction, but this vector has a larger magnitude than this one. So these are 2 different vectors, right? If I put another vector over here like this guy actually is moving in the same direction as him, and it looks like he's moving the same length. So these 2 vectors are actually the same, right? So we have a couple of different ways to think about a vector. I mean, we can visualize the vector, right, starting from a point and ending where it actually ends, right? This guy ends over here. This is what we'll call component form of a vector. Now, the component form of a vector will always start at the origin, right? And then this describes the direction that the vector is moving, and it will end after it moves this distance. So this vector would be starting at the origin, then moving in the x direction -3, and then the y direction 2 to end at this location. So this vector would actually start from here and move to this location. But as it's describing its movement, this is literally describing, if we want to translate along this vector, then that means that we want to move our points in the x direction -3, just like this vector moved, and in the y direction 2. Oh, I went down 2. I'm sorry. Up 2. -3, up 2. Right? So in this case, this vector moves -3 in the x direction up 2 units in the y direction. So if I'm translating along that vector, that means each of these ordered pairs needs to be moved -3 in the x direction and 2 in the y direction. So we'll do it visually here. And we'll say that this guy moves left 3 up 2 to its new location. So this will be A prime. Left 3 up 2 to its new location. Right? So here's my new segment. Right? If I looked at the vector, right? If I took this vector and moved him down here, he would actually move. If I moved along this vector, right, this distance in this direction, it moves the point in each of these. Because like I said, these 2 vectors are the same because they move the same distance and go in the same direction. So that means that this vector, if I put it here, maps A to its new location. If I put it here, maps B to its new location. So this is what we'll call moving it along the vector. So component form just tells us the shift, right? It tells us the shift. So basically, if I didn't want to do this visually, I can say, well, my x value of -1 is just going to be subtracted by 3 units, right? And my y value of -6 is going to be added by 2 units to get a new location, right, of -4, right, -4. And same thing, my my x value of 4 is going to be moved to the left 3 units, and my y value is going to be moved up 2 units. So this will just be, what, 1, -1? Okay. So it does the same thing as the translation equation. It's just not as bulky, right? It describes the movement of x, not that you need to take the x and do something to it. This is just describing a movement. So translating along the vector ends up just being a more simplified expression of what the translation equation is doing, right? So let's try another one. So again, we want to translate it along a vector. The vector describes, as we've already discussed, the x movement and the y movement. So having a 0 in this component form of the vector just means that we're not moving it in any way in the y direction, right? So when we take these points, which are here, we're just going to move it +3 in the x direction, nowhere in the y direction. So this is just going to be a horizontal translation, 3 units to the right. So 1, 2, 3 puts s prime over here. 1, 2, 3, no movements up or down, right? That's why the y value is 0. And then 1, 2, 3. And then again, here's my new shape. Visually, I can see that it works out, that I have this rigid shift to its new location, right? If I wanted to just work with the ordered pairs, each of the ordered pairs, each of the x's are going to be added by 3. The y is going to add to nothing, to 0, right? So not much going on, right? Now I can just add these together. So what do we got? -1, 1, 2, 0, 0, -4, right? And if I looked at here, 0, -4, 2, 0, -1, 1, it's looking good, right? They all map, whether you want to do it visually or through the movement of the vector. Okay. So in some cases, maybe we're given the figure that we want to translate, and they show us the vector, right? They can just say, translate below along the vector. Now, we know, right, as we just discussed, that a vector starts somewhere and ends somewhere. So I want to make note of where it begins and where it ends so I can verify its movement, and that's how we're going to move here. So this guy starts here, and he's going to go to the right 3 units and down 2 units, right? So I'm going to translate each of my points, right 3 units, down 2 units. So 1, 2, 3, down 2, right? 1, 2, 3, down 2. And here is my new A prime and B prime. So again, the vector describes the movement, right? If I wanted to write this in a component form, I would say right 3, down 2. So if I wanted to make the component form and then use the component form on these ordered pairs, I can come out here and write them out if I wanted to, right? That is definitely an option here. Okay. All right, so again, same idea. We have our line segment over here. I want to know where this is moving. So I see that it starts here at this point, it ends here at this point. So it's going up and right. I'm sorry, left. So it's going to go what? Left 2, up 4. Now sometimes people will say, think of this like a slope. So they'll say, all right, well, whatever my point is, I'm going to move him 1, 2, 3, 4. So if you think of this like a rise over run, right? And if I say I'm going to go up 4 and then left 2, and then what tends to happen is you say, well, up 4 over 2, that's the same as 2 over 1, right? So I'm just going to move these guys up 2 over 1. Now that moves it in the same direction, but remember a vector has a magnitude, a certain distance. So this is the distance that we want to travel. Don't reduce this distance as a rise over run, because reducing it means that we're not going to move it the same distance along that direction. So if you see that this thing goes up 4 and left 2, then you need to take these left 4 and up 2. Don't reduce them. So that's exactly what I'm going to do, right? Starting here, left, up 4, left 2. 1, 2, 3, 4, 1, 2. So this is C prime. Up 4, 1, 2, 3, 4, left 2. So again, if I were to move this vector, you can see that it will match up each of the original points to its image, right? Okay. So again, it doesn't matter if you do these visually or more mathematically, right? As we move through a lot of these other transformations of points, sometimes it might be better to work the numbers just because, again, just to recap, if it falls off of the coordinate plane, then taking a visual approach might be a little too hard because the points are very spread out and things like that. So, falling back on some of these ideas may not be a bad idea. Okay?